Right. So few examples to do with silvering of lenses and combination of lens and mirror, etc. So for example, if we have something like this, we have a concave or concavo-convex lens which has been silvered from this side. So this is concavo-convex lens with radii, let's say 45 centimeters, 60 centimeters, and refractive index of glass equal to 1.5. And this is silvered from this side. And now we keep a point object on its principal axis at some kind of distance. Let's say this distance is, let's say 90 centimeters. We want to find the position and nature of the image. By nature, we mean real or imaginary. So this is a typical type of situation in which we would be better served by using the formula to convert the given lens silvered from one side into an equivalent mirror, rather than solve it as a combination of events, refraction, then reflection, then again refraction. You can do that also, but it will just become very lengthy. So much better here is to just use the combination of lens and mirror concept. So we will just use this concept over here, that this thing silvered from here is actually equivalent to this kind of a lens in contact with a mirror like this. This becomes an equivalent mirror given by the focal length 1/f equivalent. In Cartesian sign convention, it is with algebraic sign. This way. Right, so just try this by this method now. And then of course you can use the mirror formula to find the position of the image. Yes, so it's a real image at a position of how much? So first you can tell me how much the equivalent focal length is, right, by that method. So as far as the lens is concerned, it should be 60 centimeters, it should be 45 centimeters. So it has an power or inverse of focal length. So this much. So as you can see, the lens is a converging lens of focal length. (360 centimeters). Now, when you silver it from one side, it becomes equivalent to the converging lens in contact with the silvered lens is equivalent to the converging lens focal length 360 in contact with concave mirror of radius 45 centimeters. So focal length of the mirror is minus of 22.5 centimeters. Right. So that thing now becomes equivalent to a mirror minus 2 upon focal length of the lens plus 1 upon focal length of this mirror. So that means that is an equivalent mirror like this of focal length 20 centimeters. Okay. So now when we have kept the object, so first of all, just make sure you are clear with this whole calculation. When we come back to, yes, Ganesh, very good, that's correct. Right, so Somadeep, Ganesh, you got it correct. Now you are keeping the object at a distance of 90 centimeters. So this situation is equivalent to this situation. So we have 1 by v plus 1 by u is equal to 1 by f with sign convention. So 1 by v plus 1 upon minus 90 is equal to 1 upon minus 10. So v becomes minus of 180 by 7. That is approximately minus. This. Okay. So we get a real image approximately 25.7 centimeters in front. Now, just as a practice, I want you to also calculate this by the single events method. So also verify this by fundamental method. That is this kind of method. The light coming refracts, reflects, refracts. Okay. So refraction from air to glass, followed by reflection, followed by refraction from glass to air. Just verified by solving by this method. Yes, Uday, so the answer is correct. Somadeep and Ganesh also, you got the right answers. Okay, so Okay, so if we solve by this method, the first event we'll be getting is refraction from air to glass. Object O, so we'll take U as minus 90 centimeters. Image I1, let's say, so we'll take B as B1, and the radius in this side 60 centimeters, so minus 60 centimeters with proper sign convention. So mu2, that is 1.5 by B, minus mu1, that is 1 by U, is equal to mu2 minus mu1 by R. So we get 1.5 by V1 is equal to minus of 1 by 120 plus 90. So we get V1 as minus of 3 into 180 by 7. Okay. So this is our V1. That means what is happening? This slide is bending a little bit like this. It has to be coming from somewhere here. So this, go through this once, seems to be correct. So the more important thing for us is 1 by V1, which will be minus 7 by 5. Now the second event is reflection. For that, the object is I1. So we substitute U as V1, and the image is I2. We substitute V as V2, and the mirror have a radius of minus 45 centimeters. So 1 by V plus 1 by U is equal to 2 by R. So we get this as the second image position. So back in the ray diagram, something like this is happening. Now for our third refraction, or third event, the situation is very interesting. This is the case. It's a virtual object actually, but light is coming from this side. So we will not change the sign convention. We keep it the same. Final image. So mu2 by V minus mu1 by U is equal to mu2 minus mu1 by R. So 1 by V2 we had got over there as minus 17 by 540, not 1 by 1. So we get 1 by b equal to 1 by 120 plus, sorry, minus 17 by 1. Minus 17 by 540. That same value that we got. This becomes the position of the final image. So this kind of thing is just for practice of sign convention and applications. These days, pending some behavior, let's say, give the final image. But as you can see, it's not really feasible to do such a lengthy calculation in the exam level. So that's why that direct formula is very important to remember. Okay, people, so hope you are clear with this. Okay, now let's look at a situation based on what we learned last time about the prism. So this is a plane mirror, and this is a thin prism with this angle equal to, let us say, 4 degrees, and refractive index of glass as 1.5. This is like the normal to the mirror. Now, if we have a ray of light which is incident parallel to this normal, so you have to trace the ray diagram and show the ray emergent. Trace the ray diagram further, showing the emergent ray and calculate the total angular deviation. The net angular deviation, that kind of thing, by the system. Just try this out. This incident ray is parallel to this normal axis. Ashish, it will undergo a refraction one more time from the prism. So it is first prism, then mirror, then again prism. Okay, so let's understand what's happening here. So it's going to emerge out here with an angular deviation of 2 degrees. So this delta 1, let's say. So delta 1 will be mu minus 1 into angle of the prism, that one. It will be 2 degrees. Then it is making an angle of incidence equal to delta 1. So next suffer a deviation like this, delta 2. So delta 1 was clockwise. Delta 2 will also be, yes, correct. 180 minus I. So that is, sorry, 180 minus 2I. So that is 176 degrees clockwise. Now, what kind of deviation it will suffer here? Will it suffer clockwise or anti-clockwise? That's the main thing you have to understand here, that emerges out this side. Anti-clockwise. So let's just try and understand this. So it will suffer deviation like this. Have an anti-clockwise deviation. Have a 2-degree deviation, but that will be anti-clockwise. Understood why this should be anti-clockwise? So your net deviation become how much? 2-degree clockwise, 176-degree clockwise, and then 2 degrees anti-clockwise. It will be 176 degrees clockwise. Yeah, so Ganesh, for that you have to understand the behavior of the prism. Let's say in one case, so light is like this. Delta 1 like this. In this case, like this. So in another case, if light is incident like this, that is why it is coming out like this is because just apply reversibility to this ray now. So if this ray was incident like this, it would have suffered deviation like this now. So we can, go back to our more fundamental kind of situation. So we have a ray of light incident like this. So if we drop a normal over here, it will bend towards the normal. Like this. And now here it should bend away from the normal. It should come out something like this. Let's make a better diagram and try to understand this. Now this was to draw vertically here. This is 2 degrees. And this was also 2 degrees. So this is a normal incidence. So it passes undeviated. Here. And then right, so this is what it should be doing. So over here, you can actually do a manual calculation that refractive index of glass into sin I would be refractive index of A into sin R. So this is 3/2 I, approximately R. Okay. So 3/2 into 4 degrees, approximately R. So R is approximately 6 degrees. So if R is approximately 6 degrees, then deviation is R minus I anti-clockwise. So it is approximately 2 degrees anti-clockwise. So this is the deviation because of the secondary function. So guys, hope this is clear. Ganesh, is making sense now? So the net deviation was 176. I'll take you back to the so once you understand that the third event or the second time it goes through this, it is anti-clockwise and not clockwise, then you can see that okay people, so hope this is clear to all of you. Okay, now next up we will do one slightly different situation, which is specifically for JEE advanced type of thing. If you have a medium with variable refractive index, okay, then how the deviation happens. So this calculation is clear to all of you. Next we look at situation where we have a medium with continuously varying refractive index. So what happens in such a this thing is that light continuously bends. Okay. So a beam of light will have a sort of curved trajectory. As you know, with the case of mirage effect and all that. Okay. So for example, if we have a situation where this is a medium suppose your refractive index is such that refractive index is increasing with y increasing. And now suppose you have a beam of light incident over here. So how its trajectory will be? So you can see that this side, so you can treat at the origin an interface between a slightly denser medium and a slightly thinner medium. So light will bend in at critical angle. If it bends in, then further it is denser. So as you keep going up, it keeps bending in. It will take this kind of a path. And the concept we use here is that at any arbitrary position, let's say x comma y, if you draw this as the angle of refraction as it is bending in. Now you can compare that angle of refraction with the instantaneous tangent at this point. So the slope, which is dy by dx, is equal to tan theta. Okay. And you can see over here that this is where the angle of refraction at that point is equal to 90 minus theta. Because this angle is theta. So the refractive index at that point into sine r be equal to refractive index at any other point sin r prime. This is the general Snell's law. Because basically what does Snell's law say? That okay, n1 sin theta 1 is equal to n2 sin theta 2 is equal to, like, if there's a series of events, that is equal to some nx sin theta x. Okay. So here we are just taking any two arbitrary points where the angle is r and r prime and the y coordinate is y and y prime. Now in this you can select y prime as 0. So the angle over here, it's a normal incidence, is tending to 90 degrees. So what will happen here is our general equation will be refractive index as a function of y into sin r, which was nothing but sin 90 minus theta, will become whatever the refractive index is at 0 into sin 90. This is a concept. So we have refractive index as a function of y into cos theta is equal to whatever this n at 0 was. And we have tan theta is equal to dy by dx. Cos theta we can write as 1 upon square root of 1 plus and now we can solve this, whatever that function is. This is some kind of function of y. So we will solve this to get a differential equation in dy by dx. And then next thing is we will integrate that to get y as some kind of function of x. So that will give us, but the cycloid or not, we can't tell. It depends on the function. So that will give us the equation of trajectory of line. Okay. So for example, now typically you will be given a function which is easy to solve. So for example, that refractive index as a function of y is something like this. It is square root of 1 plus y square by e square, where e is a constant. Then you can see that differential equation that we had, that ny into 1 upon square root of 1 plus dy by dx whole square is equal to n naught, becomes something like this, square root of 1 plus y square by e square. And in fact, you can see from this that we can this as a function also n naught is 1 because y's value is 0 over there. So this side becomes 1. So further, this becomes very easy to solve. We have square root of 1 plus y square by e square is just square root of 1 plus dy by dx whole square. So that means dy by dx is y by e plus minus 1. You can integrate this and you will get that exponential value. So anyway, this is just one arbitrary example. So I'll give you something more to solve also. But first of all, you understand the method. In the method, we are using a sort of continuous application of this thing, Snell's law. This one. Continuous application. So for this equation, now what we'll do is on the LHS, substitute an arbitrary point x comma y in the trajectory. Okay. Whereas on the RHS, we substitute a known point. In this case, the origin, where we can see the rays entering like this parallel to the x-axis. It's that kind of stuff. So this is the general method that we apply. So I just do this. Let's make a note of the general method here, then we'll discuss a particular problem. Yeah, don't worry, Sudhir. I'll explain to you what a differential equation is. Just an equation which has some derivative term like dy by dx. We have solved many differential equations before. Okay, so I'll just explain the concept of slope versus, in this case, what the angle of incidence or the angle of refraction is. So if light is following a bending trajectory like this over here, now you take any arbitrary point in the trajectory of the light like this, and at that point you draw a tangent. So what is happening? The medium is such that you can think, because your refractive index is a function of y, it's increasing this way. So you can think of, at every point there is a boundary between y and y plus dy. So the region having y plus dy has a greater refractive index. So light is bending towards the normal. So over here, this is the angle of refraction. Okay. Whereas this is nothing but theta. So when you have that ny into sine r is equal to n1 into sine r1 or any such thing, which is a constant. So basically you are solving this term, that the continuous function into sine r at that point, which is varying continuously, their product is a constant. That is the equation we are solving over here. Okay, and next thing is just calculus over there. So you can see that r is 90 minus theta. So sine r becomes cos theta, which can be written as 1 upon square root 1 plus tan square theta. And tan theta is nothing but dy by dx. Tan theta is the instantaneous slope. So that is how you are getting a relation in dy by dx and this ny, whatever function n is of y. So that kind of an equation is called a differential equation. Any equation which has a derivative term is called a differential, and it needs to be integrated to solve for y as a function of x. Okay. So the first example we took was this one. Suppose n was a function of y like this. So now we treat this like one example itself, and you can see how the solution will work out. You can see n is increasing with y. This is a case where the diagram will look like this, just like the earlier diagram. Now we want to find out the exact trajectory for a light beam that enters at the origin with what we call a grazing incidence. यहाँ पे incident light है. So we know that will keep bending towards the north, going this way. We want to find out what this path is, as y is a function of x. So this is what we end up solving. So this is the sum. Now further here, when we are opening the bracket, why we are taking dy by dx is positive of y value, because we can see that dy by dx is positive everywhere and y is also positive everywhere. So we won't take the negative after opening the screen. And then we can of course put the limits that at x equal to 0, the value of y was 0. And some y equals some x. Okay, so let me give you another example to solve yourself as a variation of this. So now we have this situation where refractive index in a region is actually varying as a function of x. This is a variation of that problem. There it was varying with y. Here it is varying as x. Like this. So the refractive index in a region where x is greater than equal to 0, y is greater than equal to 0, and z is greater than equal to 0. So z we can take as the entire z axis. Varies along the x axis. So now in this region, this would be basically this region, this entire first quadrant, okay, with z coming out and going in indefinitely. So don't have to worry about the z quadrant. Now at the origin, we have this time a beam of light which is incident parallel to the y-axis. So this is our incident line. So what we have to do here is make a rough trace its path and find its equation of trajectory, that is y as some kind of function of x. So this is now just like a variation of that, where refractive index is varying with x-axis instead of y-axis. So it will bend in a slightly different way, which you can work on. Just try this out, people. Okay, so anybody getting Acha, Ganesh, you send the integral on WhatsApp. I'll just check it. Just a moment. Okay, so here, yeah, Ganesh will get something like that. That's correct, what you said. So here it will keep bending towards the normal. Okay, so the path will be in general something like this. So now if we take an arbitrary point, x comma y, and we draw a tangent at this point, we can see that this angle theta. Now this time what is happening? Refractive index is varying with the x-axis. Okay. So you have to think of the layers of the medium like this. So the normal is actually this one. So theta only is our angle of refraction or angle of incidence, whatever. So this theta here is the angle of incidence or refraction, whatever we are considering. Okay. So we have mu sine theta is equal to mu naught sine theta naught, like this. And we have, of course, tan theta is equal to dy by dx. So we have this. So we have mu, which is that function, 1 upon 1 minus x by a into sine theta, which can be written as tan theta upon square root of 1 plus tan square theta is equal to sine 90. Because over here you can see the angle of incidence is 90 degrees. So this becomes our equation. Okay. Or rather, this is mu naught actually. Okay, so solving this equation now will give us this. There will be a mu naught over here also. That mu naught cancels both sides. So we have dy by dx upon square root of 1 plus dy by dx whole square is equal to 1 minus x by e. This kind of equation we are getting. Yes, Ganesh, I think this is the equation you have also sent. Okay. Now it's a question of how we solve this differential equation. Okay, so for that there's a bit of trick involved. So just cross multiply. So dy is 1 minus x by a upon square root of 1 minus x by a whole square. Dx. Okay. Now we want to integrate this. Yeah, it's a bit of a tricky differential equation, but don't worry, you will be doing all this in calculus very soon in maths, so you will learn how to solve this. So now in this, actually what we do is we substitute 1 minus x by a as some new variable, suppose z. Okay. So dx becomes minus a dz. Just differentiate both sides. Okay. And the equation becomes y on this side is integral of minus a will come outside. Okay. Z dz upon square root of 1 minus z square. First of all, become like this. Alright. This is clear. Now it must be pretty clear how to solve it. Put resubstitute again 1 minus z square as something theta. Okay. So z dz becomes minus d theta. Or you can even substitute this as theta square. So it will be even easier to solve. So this will become z dz, which is your numerator, will become minus 2 theta, oh sorry, minus theta d theta. So that minus minus sign cancels out. So you have theta d theta upon theta, x equal to 0 to x equal to x. So that becomes y is equal to just theta from x equal to 0 to x equal to x. So that is square root of 1 minus z square from x equal to 0 to x equal to x. So that is nothing but y is equal to square root of 1 minus, now what was z? Z was 1 minus x by e from x equal to 0 to x equal to x. So you see, you will get so later in calculus you learn that we could have just done a direct substitution here. We could have substituted 1 minus x by a whole square as theta square. Okay. So then this thing minus 2 times 1 minus x by a into minus 1 by e. There's an e outside. That's what I was forgetting. That's why dimensionally our answer is not coming correct. Okay. So this is 2 theta d theta by dx. Okay. So we could have just substituted 1 minus x by a dx as e theta d theta. So this substitution can be done directly actually. So all these steps can be avoided. We can directly substitute this over here, and that will bring us to that last step directly, where we have integrated in terms of theta. So we just substitute this. So we have done a double substitution, but we could have done it as a single substitution by using this. How is the differential equation term equal to x by a in the initial steps? नहीं, इसमें देखो क्या कर रहे हैं ना, we are substituting this thing. We are substituting this mu sine theta is equal to mu naught sine theta naught. So mu naught sine theta naught was nothing but mu naught into sine 90, and this side it is mu naught this thing. Okay. So then we are getting this relation. Tan theta को dy by dx substitute करके. Now we are whole squaring this. Cross multiplying and solving for dy by dx in terms of x. Okay, understood? So we just cross multiplying this and solving for dy by dx. So I've skipped a few steps here. There's a bit of algebra involved from here to here. And the main thing is this. Okay. So the direct way of solving this using a single substitution would be this, which is on your right side. But I've taken the more easy to understand method. That first step, I can see that this terms, this is a whole square term, so its derivative is of this type. So if I just substitute this as some z, it's a very simple thing. It's like a z dz divided by root of 1 minus z square kind of thing. So only thing is in my final answer there's another extra e which I've forgotten to substitute over here. An extra e term here, which will keep coming everywhere. Substitute that as y by e. Like this. So ultimately, this just became a maths problem, nothing else. Okay. Alright, so hope the steps up to this substitution are clear. And then the next substitution, you take 1 minus z square as theta square, so that your numerator will become theta and your denominator will be of the form theta d theta. So ultimately, this cancels out. It's a very simple integration. So that's what I was saying. I could have come to this step directly. Okay, we could have come to this step directly if in the beginning only we would have used this substitution which I had shown over here. Then I would have come to this step directly if I had used this substitution. But right now, since you haven't done, probably integration in maths fully, so this kind of direct substitution it might not occur to you. So go by this kind of method. Okay, so there are functions which are easier to handle. I've just given this you as a complicated example. Okay. As a practice example, later you can do one more question. An example for homework. You do an example where again refractive index is varying with the y-axis. Okay. That one is usually easier compared to the x-axis. So in this region, we have refractive index varying according to this formula. Square root of 1 plus y by e, where e is a constant. And again, we have light incident parallel to the x-axis or normal incidence, sorry, or grazing incidence at the origin. Okay, so this will bend and go like this. And same thing, you have to find the trajectory and all. You can see this will give you an easy integration. So this you have to solve by the first method which I showed you, where that theta was actually the complement of the angle of incidence or refraction at any point. So you have to use that thing. that your sin I at any point or sin r at any point, whichever you take, will be equal to cos of theta instead of sin theta. So that kind of method. So you can try this also later. Okay, now next example I want to discuss is bit to do with combination of lenses, but slightly different kind of combination. So we have this situation. We have a convex lens and now we have placed over here a concave lens, but the concave lens is placed like this. Where its principal axis is this one. So this is a thin concave lens of focal length f, and this is like this. And the pole to pole distance, that is this distance, is equal to twice the focal length magnitude. Okay, so this is the situation over here. Now we have paraxial light parallel to the first one's principal axis incident over here. So we have light coming from some distant source parallel to the principal axis like this. So we have to find the position of the image, final image. So an observer is somewhere here, let's say. So where is the final image seen? You have to assume alpha is a small angle here. Alpha is not a very large angle. So alpha is a small angle such that you are still always dealing with paraxial rays. Okay. So hint to you is that you will have to use the concept of magnification here. Yeah, size sin alpha by 2. No, it will be a point image only, Ganesh. But the thing is, the position will be determined. So what we have to understand is this position is the common focal point. I mean, is the focal point for the first one. Okay. Had this been the principal axis for the second one, would have been the focal point of this also. So anyway, so the first image is produced here. Okay. So this is your I1. Now this will become the object for the second one. So the object for the second one is not on the principal axis. That's the thing you have to understand. Yes, Ashish, that is the case. Okay. So this is the image for the first one. That becomes the object for the second one. Okay. So now for the second one, it is like this is the principal axis. Okay. This is alpha. So it's a heighted object. It has h like this. And because this whole thing is 2f, so this is equal to f. Because this was equal to f. Okay. So this becomes how much? This becomes f cos alpha. And this height becomes f sin alpha. Okay. So now you'll see something very interesting. The second image will be produced somewhere here. It will be at h prime, something like this. Okay. Where this will be the value of v. So we'll see for refraction by the concave lens, we have to take u as minus of f cos alpha and f as minus of f. Yeah, you can approximate the values of sin alpha and cos alpha. So 1 by v plus 1 by u is equal to 1 by f. So if alpha is a small angle, then sin alpha can be approximated as alpha and cos alpha can be approximated as 1 minus alpha square by 2. Got something wrong here. V should be a negative quantity. Oh, sorry. I've used this formula wrong. Minus. What I thought. Minus. Okay. So it is now like for the concave mirror, concave lens, this is what is happening, right? The object which is here will produce an image somewhere here. Okay, but interestingly, you'll see that image and object lie on this principal axis of the original lens. So anyway, this distance is suppose your y, and this was your x suppose. What you have seen is that x was u cos alpha, and y is now f cos alpha. And this is now f cos alpha upon 1 plus cos alpha, like this. So if alpha is very small, this is almost tending to f by 2. So small alpha is almost tending to f, and is almost tending to f by 2. And this h prime magnification will be v by u. In this case, it is plus this thing y by x. So h prime will be equal to h into so it is f sine theta, so f sine alpha upon 1 plus cos alpha. So anyway, so your final ray diagram will look something like this. So light incident like this is producing your first image somewhere here, and that light going further like this is diverging such that when you produce this back, it's giving you your final image somewhere. And over there, if you want to calculate this distance now, from this point, you want to calculate this distance, let's say this one. That again will come from trigonometry. Just a moment, people, I'll reshare the board. Yeah, so we want to calculate this this distance here, this one, from the I2 to the second pole, that one, that distance is d, suppose. So again, that will look something like this. Second image and the second pole. Such a thing that this was your y. So your d will be equal to y upon cos alpha. So that will become f upon 1 plus cos alpha. This kind of thing. All right. So hope it is clear why I1 and I2 are lying on the same common line. Because to show it here properly to you in this moment. Why I1 and I2 are lying on that common line is because of this. Suppose this is the principal axis of this one. So what will happen is I1 was somewhere here and this was the same. So I2 will have to be somewhere such that it has to be here, because this angle is common. It's like, the ray of light going from here, this goes undeviated. So I2 has to lie on this. And any other ray of light that will bend away. Such that when you produce these back, they will intersect at this point. So that is why I1 and I2 lie on this same line. The I2 and I1. These are the relations. Okay. Yeah, so cos alpha we can approximate as 1. That's why I said so it is nearly f by 2 in that case. Y is nearly f by 2. Okay, so hope this is fully clear. No, the distance of the final image D will be this thing. It is f by 2. Now see, if alpha is very small, then there's hardly any difference between this distance d and this distance y. See, here, this will also be f by 2, approximately f by 2. If alpha is very small. Actually, a more exact value will be like this. D will be tending to f upon 2 minus alpha square by 2, where alpha should be substituted in radians. So then this thing can also become sufficiently negligible. So further this becomes f by 2. Okay, the main thing was how you deal with the fact that the principal axes are not same or not parallel to each other. So this is how you deal with it. Okay. And of course, you also know a situation where if the principal axes are parallel but not common, how to deal with it. That is a much easier situation. If you have something like this, that this one's principal axis is this, and the other one's principal axis is parallel to it but not common. It becomes the easier version of this question. इसका principal axis अगर ऐसा है, it's very simple. Okay, and again, suppose you had the same situation, and there's no this thing involved. It's very simple. This will give you an image here. Now this becomes an object like this, so its image will be somewhere here. So this will be I1, this will be I2. Okay. All right. Now, next up we will look at the last section of the theory part, which is about dispersion of light. By prism. Now again, we will be treating this like experimental result kind of thing. Okay, so what happens is the phenomena of dispersion itself is to do with the fact that when you have some refractive medium, the refractive index is actually a function of wavelength. So what happens is white light incident, it splits into colors. Splits into colors such that the maximum deviation happens for violet and the minimum deviation happens for red. In the spectrum, this has minimum deviation and this has maximum deviation. This is an observed phenomena. We can treat it like an observation right now, because we can't really get into the theory of why that happens. That has to do with refraction at wave level, and that goes beyond the scope of our syllabus over here. So if there is white light, which consists of all the wavelengths, violet, indigo, blue, green, yellow, orange, red, included in that single beam of light. After refraction, it splits such that the maximum deviation is for red and the minimum deviation is for violet. Sorry, the other way around. Minimum is for red. So that means that refractive index for violet is maximum and refractive index for red is minimum. And the mean refractive index or the average refractive index is either taken as refractive index of yellow, or if that data is missing, we can take it as more or less equal to the arithmetic mean of this. Okay. So this is refractive index for violet wavelength. This is for red wavelength. So now coming to a prism, dispersion by a prism, there are certain terms that we define and we should know. Okay. So this splits here itself into the component colors. This, okay. Right, so if white light is incident like this is a phenomena of this thing, dispersion that you can see. Now if we produce the incident white light beam forward, okay, then this quantity here is the deviation for red, and this quantity here is the deviation for violet. Okay. So there are certain terms that we define, and we define angular dispersion as this. The difference in the angular deviation of violet and the angular deviation for red. And we define mean dispersion as so that is or you can write it as approximately. So these are two technical terms that we know: angular dispersion and mean dispersion. Just note down this definition, then we'll see some more formulae. Now this is not specifically only for JEE mains. This is part of the JEE advanced syllabus also. But typically what I've seen is it's just formula based. So your JEE advanced doesn't have questions based on this. The questions are typically from this part come only at JEE mains level. Now the next thing is that for a thin prism, we have a thin prism which is having angle A, small angle, and is made of glass which has refractive index of violet, refractive index of red, and refractive index of yellow. All these three quantities are known. Then for this thin prism, this thing, the angular deviation is refractive index minus 1 into angle of the beam. So for the individual beams also it is like this. So therefore, angular dispersion, so I think is denoted typically with the symbol omega, is becomes the difference of refractive index. Violet having a larger refractive index into angular, and mean dispersion, or this is also called dispersive power. That becomes okay. So these are just couple of formula to remember, where it can, in case mu of violet is not known, sorry, mu of yellow is not known separately, then approximate it as the arithmetic mean for violet and red. So in our formula-based questions, this becomes the important part. These two formulas. This one and this one. Okay, so this is just about definition. Now, based on this, depending on what we are trying to achieve using the properties of the prism, there are two types of combinations of prisms that are used. Yeah, Ganesh, ray optics is more or less done. Now, the first type of combination is called a chromatic combination. We will be doing waves. I'll tell you at the end of the class. So the chromatic combination, the concept is that it creates deviation without dispersion. In this, we place two prisms like this now. Typically, we use thin prisms. So this prism has angle of the prism A and refractive indexes like this, and this one has angle of the prism E prime and refractive indices like this. The second one. So what we want here is that white light incident should emerge from the combination as white light only, but with obviously some kind of dispersion, with some kind of deviation. Suppose incident white light is coming out like this. So there is some net deviation, but white light emerges as white light. So for that, what should happen is the splitting of light that has happened here, it should create a recombination in the second prism. Just a moment. So this splitting has happened in the first prism. It should exactly get reversed in the second prism. This is what should happen. So you understand, it's something like reversibility. You just imagine reversibility over here. That suppose light was coming from this side, then this would happen. So for this first one, you can see that this here is the angular dispersion. For the second one, this reverse is the angular dispersion. So we produce this final light back. So this is like for this to happen, the angular dispersion of the first one should cancel with the angular dispersion of the second. So mu v minus mu r into A should be equal to mu v prime minus mu r prime for this. So the condition is that the ratio of the angle of the prisms should be the ratio of these terms. So the condition for dispersion or net dispersion to be 0. And as a result of this, the net deviation that we have will be the deviation due to the first prism minus the deviation because of the second prism. So this will be like the mean deviation. So it will be mu of yellow minus 1 into A minus of so this is the amount of net deviation that we achieve. So this term should not be 0 because we want this. But this condition should be satisfied so that there is no net dispersion. But there is deviation. So this is the first type of combination of prisms, which is called the achromatic combination. And the second type of combination of prisms is one where we have dispersion without deviation. So we want the light to emerge without any angular deviation, but just split into the colors, that kind of situation. So white light incident here should split in such a way that it emerges something like this. It emerges parallel. Parallel. So for this to happen, what should happen is that the net deviation should cancel. This is E and refractive index mu, and this is E prime and refractive index mu prime. The net deviation should be 0. That means mu minus 1 into E equal to mu prime minus 1 into E prime. Where this mu is this thing, it is mu of yellow or approximately mu of violet plus mu of red by 2. It's simple. Okay. Whereas there will be net dispersion such that comes. So this is the formula for the net angular dispersion, and this above becomes the condition for deviation to be zero. This is the condition for net deviation be zero, but there will be dispersion. So this is that type of combination which produces dispersion but without deviation. And the earlier one was the combination which produces the reverse of this. It produces deviation without dispersion. So that is called the achromatic combination. This is called the chromatic combination. Okay, people. So this last part, the dispersion and spectra part, you can go through the section in HC Verma. It will give you more than enough theory information that you require for your JEE mains level, plus also for your board level. There will be some general things also discussed about dispersion, which I have not got into here. But what you require for your JEE mains level formula-based questions, that is what I've given you. Okay. So, I mean, typically for JEE, concentrate more on the combination of lenses, mirrors, critical angle, refractive index, refraction at spherical surface, all those kind of things, the numerical type of application. But you should know this also because one or two questions, if they come, you can easily score them. Okay. So with this, we complete geometrical optics. So the next topic for us is going to be waves. Okay, so yeah, dispersion is not really asked in advance. It is not one of the specially mentioned topics in JEE main, so it's strictly not out of advanced syllabus, okay. But it's typically not asked in advance. Whereas optical instruments is actually excluded from advanced syllabus. It is just specially included in the JEE main syllabus. Yeah. Now about the next topic, we have to go back to 11th syllabus and discuss waves. So we will be starting with transverse waves and moving on to sound. So waves and sound will be the next topic, followed by wave optics. Okay. So hope that is clear. Okay. So next lecture we will start with this. But if you have any doubts in optics, you can send me in between. And I will send you some hints and things. And if required, I will discuss those in the next lecture. Okay. Right. So that's it for today, people. Stay safe, and I'll send you the recording and the whiteboard also. Yeah, Uday, actually, to answer your question, Erudov optics is not so suitable for JEE level questions. It is better you do optics from DC Pandey. DC Pandey has a booklet, I mean, has one of these books in his set, Optics and Modern Physics. That will give you more relevant type of questions for JEE level. Erudov, it's better if you stick to mechanics, electrostatics, magnetism, electromagnetic induction, even some part of thermodynamics. But waves and optics, not so much.